We've talked about using a Riemann sum as an estimate of the area between a curve and the x-axis. We've also talked about if you take the limit as the number of subintervals of a Riemann sum goes to infinity, that gives you the definite integral. Today what we're going to do is look at something that the AP exam used to not ask. It's only been in the last 5 or so years that they've started asking this question. And I honestly don't know how often they ask it because, well, I'm not allowed to talk about the multiple choice questions, and it's almost always a multiple choice question. Where they're asking you to write Riemann sums or write a definite integral from a Riemann sum or vice versa. So we're going to start with a basic Riemann sum problem. Use a right Riemann sum with 3 equal width subdivisions to estimate the area under the curve f of x is equal to 5 plus sine of pi x over 4 from x equals 6 to x equals 12. All right, so if we're doing that, it wants us to do 3 equal width subdivisions. So the distance from 6 to 12 is the distance of 6, right? If we want each subdivision to be the same width, and we want 3 subdivisions, how wide should each subdivision be? 2. Yeah, so the width of each subdivision, if you want to be, if you want to write out what it is that we did to get it, it's 12 minus 6, that's the total width, divided by 3, the number of subdivisions, gives us that every subdivision is going to have a width of 2. So what that means is that if we're using a right-hand Riemann sum, my subdivisions go 6 to 8, 8 to 10, 10 to 12, but we're using the right side each time, so we're only using those. So in order to find the area under that rectangle, we need to know the width, which we do, and the height, which will be the value of the function at each of these 3 points, 8, 10, and 12. So that's going to be equal to 5 plus sine of 8 pi over 4 times 2 for the first rectangle. And then the next one will be plus 5 plus sine of 10 pi over 4 times 2, because that's the width, plus the height of the last one, which will be 5 plus sine of, 12 pi over 4 times 2. And at that point, we can grab a calculator and put all that in if we want to get an actual value. So 5 plus sine of 8 pi over 4, we'll just make that 2 pi. Times 2 plus 5 plus sine of 10 pi over 4 multiply that times 2, and then the quantity 5 plus sine of 3 pi times 2. And that comes out to be 32. So if we wanted the actual area under the curve from 6 to 12. Since this is always positive, we simply need to take the integral. The actual area would be the integral from 6 to 12 of 5 plus sine of pi x over 4, all times dx. So that's math 9. The integral from 6 to 12 of my integrand will be 5 plus sine of pi x divided by 4. Close that parenthesis. Yeah, it's already closed the other one with respect to x. The actual area is 31.273. For only 3 subdivisions, that's a pretty good estimate. Okay, because each one that's a pretty, if you want to think about it this way, I always think about it in terms of pixelation. It's pretty clunky, right? Every subdivision is a width 2. That's not particularly good. Now, we can make our work more general by calling the lower limit A, our upper limit B, and the width of each subdivision delta x. So in this case, the area is approximated by f of a plus delta x, right? We started off at 8, which was 2 beyond our lower limit of integration, our starting point, times delta x, then plus f of a plus 2 times delta x. We're moving over 2 subdivisions now, times delta x, and then f of a plus 3 times delta x times delta x. We can write that as a summation, as the summation is k goes from 1 to 3 of f of a plus k times delta x times delta x, where delta x in this case was equal to b minus a over 3, right? The upper minus the lower divided by how many subdivisions we're going to do. Now, we can generalize this even more by going, well, we don't have to do 3 subdivisions, which is what we're doing here. We can do any number of subdivisions. So for any number of subdivisions, the area can be approximated by the summation as k goes from 1 to n of f of a plus k times delta x. So where you started plus how many subdivisions we've moved over, times the width of each subdivision, where delta x is b minus a over n. That's a right-hand Riemann sum approximation of the area. Now, students frequently will ask, and I think it's a good question, it's like, why are we fixated on right-hand Riemann sums? Because they're slightly easier than left-hand. Not a lot. If you want to do a left-hand Riemann sum, what you would have to do is one of a couple of things, but the simplest thing to do is do the summation as k goes from 0 to n minus 1. So that on the first one, you're starting where k is 0, so you're starting at the left-hand endpoint, and you're going to end just before you get to the right-hand endpoint. Okay, you can do that. There's nothing wrong with it. The problems that have shown up on AP Central or AP Classroom have all been right-hand Riemann sums. So I think that that's the way that they're more likely to ask it. So if we want to change this from an approximation to the exact, we just let the number of subdivisions go to infinity, right? That'll smooth out the pixelation of it. So the area is exactly equal to the limit as n goes to infinity of the summation of, as k goes from 1 to n, of f of a plus k times delta x, that's moving us along each time, times delta x, which is the width. So this is the height times the width of the rectangle. That is also equal to the integral from a to b of f of x dx. Remember, that integral gives you the exact area. So what kind of problems are you going to have with these? They're going to ask you to move back and forth between one and the other. So let's look on the back. Given the integral, writing the Riemann sum is the more difficult one of the two. I mean, it just is. There's more writing and more stuff where you can go wrong. So this is equal to the limit as n goes to infinity. We want an infinite number of subdivisions of the summation as k goes from 1 to n. This summation is my incrementer of the square root of, where are we starting? 4. So the square root of 4 plus k times delta x. Well, delta x in this case is going to be 9 minus 4 over n. So that's 5 over n. So it's going to be 5 over n times k, or you'll also see it written as 5k over n. Same thing. Times, that's the height of my rectangle in a Riemann sum, times the width, which is 5 over n. Now, part of the reason that this is likely to be a multiple choice question is because there is more than one right way to write that. Tony's like, crap. So, and part of it is that the integral from 4 to 9 of the square root of x dx is the same thing as the integral from 0 to 5 of the square root of x plus 4 dx. Right? This takes the square root function and moves it and so these two, if we notice, if you substitute in 4, you've got the square root of 4. If you substitute in 0 here, you've got the square root of 4. All right, when you substitute in 5, you have the square root of 9. Here, you've also got the square root of 9. So this takes the square root function and moves it to the left 4. And notice that my limits of integration have also moved to the left 4. Okay, so you could start from this and write the Riemann sum. So this is why on the AP exam, at least, they're likely to give you a multiple choice. They'll say, which of these Riemann sums is equivalent to this integral? And just know that they can monkey around with this. You know, they can go, oh, we're gonna play around and move it left or right first. I usually, when I'm just asked to write a Riemann sum, I just do it straight from this. All right, so let's try this next one. So we'll have the limit as n goes to infinity, we want an infinite number of subdivisions of the summation as k goes from 1 to n of 3 plus, that 3 doesn't change because there's no x involved there, tangent of, all right, I'm starting at -2, plus my delta x is going to be 6 minus -2 over n, so that's 8 over n. So 8k over n. Got to close both of those parentheses, times 8 over n. And you can kind of check yourself by going, okay, if k was equal to 1, this would be 8 over n for your add-on to -2. So you're adding that much on to the -2, so you're moving over one subdivision each time. All right, one more. This gets to be kind of rote pretty quickly. So the limit as n goes to infinity of the summation as k goes from 1 to n of the natural log of, for the x, we're going to start at 1 plus my delta x is going to be 10 minus 1 over n, so that's 9 over n. So 9 over n times k, so 9k over n. Having all kinds of trouble with this. Plus 1, because that's the one that was already in there, times k over n. Oh, excuse me, times 9 over n. Notice I can simplify that to be the limit as n goes to infinity of the summation as k goes from 1 to n of the natural log of 2 plus 9k over n times 9 over n. Which, if you try to read it backwards, you're like, oh, my starting point is 2. Well, let's see what happens if we do that. That would be the integral from 2 to, my width is 9, so that's 11, of the natural log of x dx. Is that the same thing as the original? Yeah, it is the same as the original. Okay, and that's part of why, like I said, I think it's going to be a multiple choice question. So now let's go the other direction, which I think is usually, I'm going to show you an exception to it, but usually is the easier of the two. So here we have the Riemann sum, and we can pick out in here our starting point is at 3, and from our delta x, we know that the width of the whole interval is 4. Right, so that's going to be from 3 to 7. And it's just e to the x dx. I think this one, and I put this one on here because I have to think about it sometimes. This one's not as as quite as clear cut, partly because you have what looks like part of the x in two different places and they don't look the same. So you're like, well, this is, at the end I've got 7 over n, and I've got the 7 over n times k here, but here I don't. Well, that's 3 times 7 over n, right? And underneath the radical sign, it feels like it should start at 5, right? The simplest way to do that is, since this one looks like it starts at 0, go ahead and start at 0 because there's no plus anything, and just put the plus 5 underneath the radical sign. So that this would be the integral from 0 to 7 of, this part is going to be 3x, and under the fourth root we'll have 5 plus x, or x plus 5. Now, what if you're like, no, I want to start it at 5. Can you? Yes. It'd be the integral from 5 to 12 of 3 times, and this is where people make the mistake most often, it's x minus 5. Because I don't have that 5 plus in there. And then this would be the fourth root of 5, excuse me, fourth root of x dx. And the way that I check that these are the same is just to look at the value of both of them at the upper and lower endpoints. This would be 0 and that would be 5 underneath the fourth root. At 5, this is going to be 0 and this is going to be 5 under the fourth root. That's how, when I'm looking at two integrals to see, are they likely to be the same? Now, there's more to it than that, but that's a real good, easy check for something where you're like, oh, they've just moved this left or right. Okay? All right.